Good morning. Well, first I would just like to thank you and say quite an honor it is to be speaking before you today. And I would like to give a special thank you to Dr. Hisham Al-Askari, His Excellency Water Minister, as well as Dr. Ragab for helping organize this session, and my invitation by Dr. Hisham Al-Askari as well. So, as Dr. K just mentioned, NASA has a very large fleet of satellite observations. And what I'll be presenting today is just a very brief overview of how we're taking some of these observations from space and integrating them into solutions. So we like to say moving from data to decision making. And over the past few days, I've had the great pleasure of learning a lot of solutions that are being applied in North Africa and within Egypt. And we share some of those solutions and some of those ideas. So with that, I'll move on. So the Water Resources Capacity Building Program, it focuses on applying satellite observations and numerical modeling for improving water resource management. And this is realized in several different ways. Well, let's see, I'll advance this way. And as Dr. K already mentioned, the water cycle, we have this, but as our challenge here is to, as accurately as possible, study the interaction of the energy, momentum, and mass exchange between the land surface and the atmosphere. So each component of this water cycle, how can we characterize, understand, and predict each single component as frequently as possible and as accurately as possible? So you can do this in two ways. As you know, you have observations. You can put an instrument in the ground, or you can use a remote sensing technology to monitor that as well. And then, how do you estimate an observation that's 1 foot from you or 1 meter from you to 50 meters away? Well, you do that through using physical equations. And so extending that observation and hopefully making it physically consistent so that you can further characterize those states and fluxes that you're observing. I think most people are familiar with this figure. This is Moore's law. So it says every 2 years, the number of transistors in a circuit will double. Well, in fact, we've seen this advance in technology. This is the ENIAC computer. This was taken in 1946. So this is considered one of the first quote-unquote mass computers. And if I look at my cell phone, the cell phone is 230 million times faster than the ENIAC computer. So in just 72 years, we've come a great distance. Our ability to observe the Earth, our ability to capture this data and to utilize this data has rapidly advanced. In fact, in the same year, in 1946, this was the first image ever taken of the planet Earth. It's nearly 72 years ago, almost to the day. And what they did is they put a camera on a Delta II rocket, and they launched it from the White Sands Air Force Base, and they were lucky enough to get this picture. So if you advance to some of the images that Dr. K just mentioned, now we have the ability to monitor different components of the water cycle at every 3-minute temporal resolution and at spatial scales that are useful for improving our water resource management. What we're seeing here, this is not an animation. This is actually 2 observations just overlaid over each other. So one is from the NASA's Global Precipitation Mission, and the other is from the Soil Moisture Active Passive Mission. And it's not only a beautiful animation, but it's really useful for, first of all, educating and conveying the idea of precipitation memory. How is that precipitation event really realized on the land surface? Well, you see here, you see that this moisture, there's a soil moisture precipitation memory that's captured in the soil. This is very important for a number of processes. So what I've done is I've prepared a very brief talk and a few examples on some topics that I've observed this week that may be relevant for this room. So if you look at drought forecasting, the NASA Applied Sciences program is partnering with a number of agencies around the world, and one of the projects that I'm involved with is the USDA Foreign Agricultural Service Drought Forecasting. And essentially what they're responsible for doing is providing global estimates of crop forecasting. And the way they do this is they take precipitation estimates and they drive crop forecasting models. When many areas of the world, the accuracy of the precipitation data needs improvement. Now we have a direct observation of the soil moisture to drive those crop forecasting models by using SMAP. So this is an example in South Africa in 2017. So we were able to forecast not only that drought, but that the soil moisture, which is a leading indicator of drought. Once you observe the drying and the senescing of the vegetation, you've already observed, you've already witnessed, and the impact of that drought has already been realized. Now, if we take this concept of satellite observations of soil moisture and vegetation, and how do we move that into decision making? How is this useful? Well, another group that we're working with is the Agricultural Statistical Service of the USDA. And they're trying to estimate on a county by county level in the United States the yield forecast, the end of season yield. So it's a very busy chart, but essentially the warmer colors that you see here represent a higher correlation with end of season yield. So if you look here, you see we have vegetation indices on the left. So that means if you look at the center figures, in July, the warmer areas, that variable would be highly correlated with end of season yield. So we can use that observation from satellite to forecast what that yield may be. And we've done this with several other different satellite-based and hydrological model-based estimates. And what we've seen is that by using satellite observations and numerical modeling, we have estimates that compare very well with the survey-based estimates. So going out by hand and collecting these observations of end of season yield, we can match the accuracy of that by using satellites. And so this, of course, this is more efficient and possibly saves money as well. Another project I think may be of interest is this project working with the FuseNet. This is the Famine Early Warning System. This is a project that's funded by the USAID and NASA. It's called FAME. And essentially what they're doing is they're taking a collection of hydrological land surface models and merging that with climate forecasting models. And then they're calibrating this, and so they can forecast not only precipitation, but also forecast future soil moisture conditions as well. And so this was a forecast that was released in September of 2018. And so the forecast shows slightly saturated soil in this region. But the point here is that we're taking all this data and providing it to an agency and users that then they can improve their decision making from. And that's really the main business of the NASA Applied Sciences program. We've heard a lot about reservoir operation this week. Well, one project we're partnering, this work is by partnering with Thorpex and also with collaborating with the Egyptian Space Agency, NARS. So here they've taken a suite of climate forecast models with different levels of accuracy, and they're focused in different regions, and they have different forecasting times, extending from a few days to up to 15 days. Well, then they apply these to a hydrological model and a routing model. And the key here, this is a very busy slide as well, but what I'd like to highlight are the different colors that you see here. These are forecast models driven by different forecast models compared with in situ observations. So calibrating these over different basins, then you're able to increase your accuracy of those forecasted areas. This project is also working from taking these forecast models down to real-time satellite observations, combining this with a historical data perspective. And that's one of the advantages of using a long-term data records, to have a reliable anomaly in soil moisture or anomaly in river forecasting, you have to have a long-term data record. And here the key is that they're providing interactive maps and partnering with these local regional agencies. This is new work that's being done at NASA as well, and it's being they're collaborating with NARS as well. And what they're looking at, it's a very busy slide, I apologize, but it's very interesting because what you're looking at here over these major basins, you're able to characterize the dynamics of the total water storage. The total water storage, on average, would be 0. So if your terrestrial water storage anomaly is the deviation from that average. And what they've done is they've tried to isolate the main signal from that terrestrial water storage in these basins. If you look at the northern regions, I'll point the slide all the way up on the right. You see there that the black line, no, this doesn't work, the black line is actually snow, or snow water equivalent. So you can see that most of the terrestrial water storage dynamic is driven by that snow water equivalent signal. The figures on the bottom show the percentage of these fluxes that are realized in the terrestrial water storage anomaly. So you have groundwater storage, snow water equivalent, but I like to point out that soil moisture is the dominant signal in the global terrestrial water cycle. So it can be explained by 51% of that global terrestrial water storage anomaly. The NASA Applied Sciences program is also working with agencies to help them monitor and forecast flooding events. So what you see here, that we're working with the Asian Disaster Preparedness Center in Thailand, and we're able to map flooded regions. But not only can we tell where your feet may get wet from flooding, but also integrating that with socioeconomic data. The population, where are the schools, the hospitals, the roads. And we've also combined that with a hazard model. So I'd like to emphasize that this is a near real-time operational product driven by satellite that within hours of a flooding event, we're able to provide estimates of damage and US dollar amount. And that's very, very powerful information. In fact, just 2 months ago when the Laos Dam broke, we were able to provide assistance and work with the emergency responders and give them an idea of where the flooded regions were and the percentage of the population that was affected, as well as the percentage of their agriculture that was affected. If you're able to give them an estimate of hectares of rice that was inundated, that's very, very useful information. The NASA Applied Sciences program is working heavily with water quality, and Dr. Kay mentioned this in the morning. But we're working with utility managers. And this is a current study working in New York City. So some reservoirs that are sourcing New York City utilities, they're driven now, they have these water quality estimates that are provided by satellite observations. So from taking these pretty pictures and all this stuff, but then providing something that's useful for the utility managers there. Dr. Kay mentioned the groundwater, and the NASA GRACE satellite is something I really enjoy talking about, but what it does, it provides an estimate of that terrestrial water storage anomaly that I mentioned a few slides back. And if you look at this figure, this was published in Nature a few years ago. And in Northwest India, you're able to see a definite signal from groundwater pumping in Northwest India. Now, if we were just looking at soil moisture, or if we were just looking at the surface variables, and that's what you see here in the red line, that trend, a groundwater trend, would not be realized. But by integrating GRACE observations of terrestrial water storage, you see this very strong downward trend that is unsustainable at current rates of pumping. NASA is working with satellite irrigation management support, and there's a project called SIMS, and they're working with the California Department of Water Resources and the Water Growers Association in California. And the idea here is to take near real-time observations and estimates of evapotranspiration and water use and water demand from plants and provide them to a cell phone for local farmers. And this is a very exciting project that's being led by Forrest Melton at NASA Ames, and he's published several papers on this. Because there's many different ways to solve the energy balance, and you can estimate evapotranspiration, or you can solve the water balance and do the same thing, or you can use reflectance from satellite. But Dr. Melton has taken several of these approaches and combined them into one feasible application and provided them to regional growers. And this shows one of the outputs from the SIMS system. Now, I started out, I talked about the ENIAC computer and all the data that we have available. This graph on the left shows the distribution volume in petabytes. NASA is embracing cloud technology, and this is one of my last slides, but what we're moving towards, especially for improving resource applications of water, is providing these data and solutions on the cloud. And I want to emphasize again that all NASA data is public, and NASA follows an open data policy. So every product, every model that I've shown on these slides is openly available and freely available to everyone. And with that, I think I'll end with this slide, and I encourage you all to visit the NASA Water Resources Applied Sciences Program website, or please talk to me. I love talking about this work, and again, it's such an honor and a pleasure to be in this room with you and to learn from you today. Thank you so much.